Welcome students. I hope you are able to get some idea about the evidence of nucleosynthesis which has been happening in the universe from the time of Big Bang. Let me quickly summarize the previous lecture where I have addressed a query that for how long the solar abundance distribution got operated. It was about 10 billion years, considering the phenomenon of cycling processes between a star and the interstellar medium. And then I have provided some information about the categorization of nucleosynthesis, which is basically the process of formation of new nucleides due to nuclear reactions. What are those three categories? Number one, primordial nucleosynthesis, which is essentially the reason for the formation of hydrogen and helium, and cosmic ray interactions, which leads to the formation of lithium, beryllium and boron, and then beyond boron, starting from carbon and beyond, stellar nucleosynthesis. Then we have seen how the discovery of Technetium 99, that is mass number, by Paul Merrill in 1952 using the observatory has changed the way researchers used to see the world. So, the view with which people were looking at the world has dramatically changed because of this discovery. See, not frequently discoveries will change the world view, but this was the one which changed the view of the world regarding the synthesis of elements in the universe, how elements got synthesized in the universe. So, in a nutshell, I wanted to convey in the previous lecture that because no isotope of the technetium is stable, and with the telescope the emission and absorption spectrum has given a clear indication of the presence of technetium. You have to understand, because it is not an astronomy course, I am not going into the details of those measurements. How that line in the spectrum was recognized or identified as technetium, those details I am not going. So, this is the limitation of my course, and as I said in the very first class, it is basically the role of nuclear physics in the stars. But yes, it was very well established that the technetium was very much present in the spectrum recorded by the telescope, which was handled by Paul Merrill. So, when we can detect the technetium, whose the half-life of the most long-lived isotope of technetium is about 4 million years ago. At first instance, you may think that 4 million years ago, 4 million years is a very big number, but at a cosmological scale, when you talk about billion years, it is very, very less. So, now, when I say now, it is basically 70 years back. So, at a cosmological scale, of course, it is same 1915 and 2021. So, now if we are able to detect the technetium, it means the synthesis is happening even now. So, it is a recently produced technetium, and later people could reproduce it with different facilities, all right. And after that, I have given some information about the one of the important applications of the isotope of technetium, that is 99 metastable state of technetium, which is widely used in medical field as a radio tracer. A radio tracer is something which is used for the diagnostic purpose. It is inserted within the body, and when it emits the radiation through some tumor or some kind of disorder in the body, the counts or the number of gamma rays will be different when you compare to the normal parts of the body. So, that change in the number of gamma rays through the disordered section and or normal section of the body will tell the presence of the disease in the body. So, that is where technetium 99 metastable state. So, what is metastable state? See, nucleus, when it has different levels, the transition from higher to lower level happens within femto or pico, sometimes microseconds. But there are a few excited states in a few nuclei whose half life is like milliseconds, seconds, minutes and hours. These are called as isomers. These are called as isomers. So, some of you who have already been taught basic physics in BSc level, you might be aware of. But if after +2 you are taking this course, I think this terminology will be useful to you. Okay. So, isomer is something which is having relatively longer half life regarding the transition from higher state to lower state. If you are aware of the concept of lasers, where metastable states are mandatory to have, then only population inversion is possible. Without metastable states, the population inversion is not possible and one cannot get the laser. That is the reason nowadays researchers are exploring to make gamma based lasers, which are termed as gazers, because now isomers are in plenty and people have gained enough knowledge about the isomers. Using these isomers which are having metastable states nature, can one produce gazer? Can laser be extended to some kind of gazer concept? That is one of the emerging areas in the nuclear field. Anyway, coming back to our course. So, this technetium 99 metastable state is produced from the molybdenum, which can be produced as part of the fission of uranium. And because molybdenum has about 2.75 days half life, within that time it is easy to ship the molybdenum to medical facilities, and this molybdenum 99 is radioactive. It is decaying to technetium 99 metastable state, and that technetium 99 metastable state is having 6 hours half life and emitting about 140 keV gamma line. You measure the intensity of this gamma line and know the disorders within the body. That is the story of technetium 99 metastable state. So, I mean, do you remember what exactly we are trying to understand at this stage? We are looking for evidences for nucleosynthesis, and one of the important evidence I have discussed, like discovery of technetium, which has changed the way researchers looked at the world. Like technetium, many elements were the discoveries of many other phenomena and many elements. When people came to know, then some beautiful work has been compiled by few astronomers, and I am going to show you the standard paper, the standard references in nuclear astrophysics. So, I strongly suggest you to go through these papers. Review of Modern Physics Journal, published in October 1957, Synthesis of Elements in Stars, okay, by Burbridge, Fowler and Hoyle. So, this combination is well known as B square FH. So, whenever you come across like B square FH paper, it means this is the one. Okay. You can see the contents: elemental abundances and nuclear structure, and physical processes involved in stellar synthesis, their place of occurrence, that means sites of these processes and what are the time scales associated with them. So, and at this time independently, A.G.W. Cameron also published similar kind of paper titled as Nuclear Reactions in Stars and Nucleogenesis, so which was published in June 1957. So, independently Cameron and B square FH, they have published these papers on nuclear astrophysics, that means mainly the cooking of elements in stars, and these papers remain references, standard references for understanding the astrophysical processes in stars. So, I strongly suggest you to go through these papers to understand how things evolved from 1957 regarding the subject of nuclear astrophysics in terms of research papers. Okay. So, though there are many other papers, thousands of papers in the field of nuclear astrophysics, I strongly suggest you to start with these two. You will get better idea about this field of nuclear astrophysics. All right. Let me because I have given a paper from 1957, let me give you a recent paper published in 2019 by Johnson. I think this I have discussed in the previous lecture also, published in Science. So, this researcher has given a beautiful representation regarding origin of elements in the solar system that we see today. Okay. See, hydrogen and helium. Hydrogen is completely shaded with pure black, then helium little bit, most of it is black, and then some other colors like yellow and green. Now, you see different elements are shaded with different colors. So, at this stage I want to only say one thing, that the elements shaded with black, they are because of the Big Bang fusion. They were formed immediately after the Big Bang, 3 minutes after the Big Bang. Okay? And elements shaded with this color is because of cosmic ray fission. Do you recollect what I have said in the previous class? Lithium, beryllium and boron, most of them have been synthesized because of the cosmic rays. What are the cosmic rays, my dear? High energy protons, Then stars, while evolving, many times they will undergo explosion, and because of the exploding of massive stars, that means stars which have huge mass, all the elements in this table, some kind of periodic table shaded with green color, they were synthesized. And white dwarfs I will discuss in today's lecture only. Okay. So, because of the explosion of some stars which are called as white dwarfs, the elements shaded with this color were synthesized. Okay. Then the explosion of star, when we use the word supernova, so supernova needs to the another kind of entity called as neutron star. The details I will not go at this stage. Because of the merging of the neutron star also, many heavy elements are formed. Like in this table, you can see the elements shaded with orange, rubidium, rhodium, okay, palladium, silver, cadmium, all these elements. And there are few elements which are formed only because of the merging of neutron stars, that is thorium, uranium 92, plutonium 94. 94 when I say here atomic number. Okay. Earlier when I said some numbers, they were mass numbers. I hope you will not be confused. Okay. Now, when low mass stars die, then some elements are synthesized like lithium, carbon, nitrogen and all other elements which are shaded with yellow color also. And very radioactive isotopes, that means nothing left from the stars, they were synthesized, and those elements are called as PO, AT, Rn, radon, francium and radium. Okay? And this Pa palladium, PM promethium, AC actinium. See, the beauty of this table is to show what kind of elements are formed from what kind of processes. So, in a nutshell, this picture, this photograph, this diagram gives you an idea the reason for the synthesis of different elements. And after going through this paper published by Johnson, published in Science in the year 2019, I am sure you will enjoy. Fine. Okay, so let us proceed. Let me share another direct evidence for nucleosynthesis in stars. What was the first direct evidence? Discovery of Technetium 99, whose half-life was whose half-life is 2.2 lakh years. Do not get confused with the mass numbers of different isotopes, right, like Technetium 97, 98. So, they have their own half-lives. So, that discovery has changed the way people looked at the synthesis of elements in stars. Another discovery, aluminum 26. What is so special about it? Aluminum that we see in daily life, its mass number is 27, it is stable. Aluminum 26 is unstable. Aluminum 26, which is unstable isotope, was discovered by the researchers, like technetium was discovered. It has some another type of story, though in terms of discovery of a unstable isotope, it is just like discovery of technetium, but aluminum has a different story. I am sure you will enjoy the story of aluminum-26. Before that, because you people are having different backgrounds, some of you might be having basic nuclear physics knowledge, which you have been taught at +2 level. Let me give you some basic information about the radioactive source. By seeing which property of the, which feature of the radioactive source, one can get the information about the source. Like, with the help of what kind of photograph or what kind of image, you can get an idea about the bones structure within a human being. X-ray, right, scanning, and you have MRI, CT scan and all those things. By seeing that photograph, you can say, okay, so this is what it looks like in your human body. Most of the information about the structure of the body, inside the structure of the body, inside the body, information can be extracted. Similarly, when a nucleus is given, radioactive nucleus, how to know what are the levels within the nucleus, what are their energies, and with what type of radioactive decay the nucleus is trying to achieve stable status. I repeat, by seeing which kind of diagram, you can get an idea about the energy levels of the radioactive isotope, half-life of the radioactive isotope, and the type of nuclear radiation emitted during the decay, because it is a radioactive nucleus, right. That diagram is called as energy level diagram. Sometimes we also use the word decay scheme or level scheme. Now, I am going to show you the level scheme of aluminum-26. Please follow me carefully. Okay. Here you see aluminum-26, this is 26, okay. This is a ground state, this is the ground state, and this is the first excited state, this is the second excited state. First excited state have 228 keV, second excited state has 417 keV, third excited state has 1058 keV excitation energy, and the lowest one is the ground state. All right. Now, what is this 5 plus 0 plus and 3 plus? Now, this is altogether a different story. Every energy level of a nucleus, see, it is very clear that atomic level or nuclear level energy is not continuous, at least in the nucleus. At the lower level, things are in discrete, right. So, this discrete levels, they have some properties. What are those properties? Each energy level has its own spin, it has its own parity. Now, if you are not aware of the words spin and parity, I will explain in separate lecture, okay. And if you are aware of this spin and parity, then it will be easy for you right now to understand. Otherwise, later when I explain you the concept of spin and parity, then you come back to this and go through this lecture again. So, spin and parity, they are the properties of the energy levels of the nucleus, by which one can understand the transitions between the levels, transition between the levels. Here aluminum-26 decay scheme, if you see, the ground state has phi plus, where phi is the spin, plus is the parity, 0 is the spin, plus is the parity, 3 is the spin, plus is the parity, okay. And the thick arrows, these two thick arrows, they denote the transition between 1058 to 228, 407 to ground state. Corresponding to this only, the experimental data is available. Now, if you start from this 1058, third excited state, when it is decaying to 417, you see gamma ray is there. This gamma ray can be detected. People have detected the gamma ray, which is coming because of the transition from 1058 to 417 keV. The energy difference between these two levels is the gamma ray energy, isn't it? 1058 minus 417 is the energy of this gamma. Now, there is a possibility that 417 to 228 keV, you see, and the transition is taking place, but no transition can take place from 228 keV to ground state, 228 keV to ground state. Why? Because from this 0 plus to 5 plus, it is not possible for the transition to occur. Why? Because of the selection rules. There is something called as selection rules. If you have a BSc background and if you have been taught nuclear physics after +2, I am sure you have been taught liquid drop model, then semi-empirical mass formula, and some of the disadvantages of this semi-empirical mass formula were addressed by shell model. In shell model, if you have learned, you should know the meaning of this spin and parity and also the selection rules. Fine. Otherwise, go through any textbook, basic textbook of nuclear physics, it will be clear to you. So, the point which I am trying to convey here is following. The transition is not possible from 228 keV to ground state. Then what is going to happen? This 228 keV state, first excited state of aluminum 26, is going to the ground state of the 26 magnesium. It is undergoing decay because it is radioisotope, it is not stable. However, the ground state of the 26 aluminum is unstable, it is unstable. So, because it is unstable, it tries to reach to the stable status. How? By undergoing decay. Which decay? Beta minus. So, beta minus, whenever you come across, it is right tilted line, and this thick line from ground state 5 plus, I am using this pen, black one, okay. 5 plus to 1809 keV of the magnesium 26, 1809 keV of magnesium 26. The ground state of aluminum 26 is decaying to the 1809 keV, which is the first excited state of the magnesium 26. The moment decay is going to the 1809 keV of magnesium 26, immediately it will de-excite to the ground state by emitting gamma ray. So, what is the energy of this gamma ray? Nothing but 1809 keV. Alright. Now, keep this in mind and let me give you salient features of this decay scheme and how it can be direct evidence for the nucleosynthesis in stars. Very interesting. See, aluminum 26 ground state to excited state of magnesium 26 is giving rise to 1809 keV gamma ray. The half-life of this decay is 7 into 10 to the power 5 years. Okay? 7 into 10 to the power 5 years. Please remember this number. Otherwise, it will be very confusing for you later. Okay? Second, aluminum 26 metastable state. Already I have explained the meaning of metastable state, because this 228 keV state in aluminum 26 is having relatively longer lifetime compared to other states. So, it is a metastable state. It has enough time to reach ground state of magnesium 26. Alright, its half-life is only 6 seconds. 6 seconds, imagine. Alright, anyway, it is reaching to the magnesium 26 only. Now, it is not in nanoseconds. Imagine. Otherwise, all other excited states in aluminum 26, if you see 417 keV, 1058 keV, which are having spin parity 1 plus, 3 plus, they are decaying to different states of magnesium 26. All of them have in nanoseconds or pico or femtoseconds, I do not know. But certainly they are not in the order of seconds, they are not metastable states. So, certainly not in nanoseconds, it is a metastable state. Okay? Why? Now, I am addressing one fundamental question. Why excited states or some energy levels of a nucleus have long half-life, which we are calling as metastable states? Because of two reasons. Number one, if there is a huge difference in the spins, is it so? In this case, you see 5 plus and 0, huge difference in the spin. In such cases, you can expect metastable state. Number two, if there is a small energy difference between the two levels, then also there is a possibility for having metastable state whose half-lives are not in nano or microseconds. Anyway, another point in this diagram, as I said, thick arrows have been observed experimentally, not thin lines. Of course, they play important role in maintaining the equilibrium conditions within the stars. Anyway, that is not our business right now. See, the selection rules inhibits, as I said earlier, the selection rules does not allow direct gamma ray de-excitation of the 228 keV isomer, 228 keV isomer. It is because of the issue with the selection rules. So, what it will do? It will decay to the ground state of magnesium 26. Now, the actual point which I am going to highlight is following. When people have detected 1809 keV gamma, people have detected 1809 keV gamma, which is coming from the excited state to ground state of magnesium 26. Now, a very important question you should ask if you are following what I am saying. Fine, researchers have detected 1809 keV gamma, it is okay. Within the star, nuclear reactions have taken place and they have formed a magnesium 26 as part of the nuclear reactions processes, and maybe magnesium 26 is formed in the first excited state, and during the excitation within micro nanoseconds it is giving 1809 keV. How it is possible to detect if this is the scenario? If magnesium is formed as part of nuclear reactions directly and magnesium is formed in the first excited state, then whatever gamma ray is coming down with energy 1809 keV, that gamma ray would have absorbed within the star within no time. It will not come out of the star because there is no time available. Now, one interesting statement I am giving: within the star, at any place within the star when nuclear reaction is happening and gamma rays are emitting, those gamma rays are not coming out. If the gamma rays because of the transition from a nucleus which is formed in the nuclear reaction. So, gamma ray energy will be immediately absorbed within the star. If it is absorbed within the star, how we can detect on Earth? But we are detecting on the Earth. What does it mean? This 1809 is not because of the population of magnesium 26, but because of the decay of aluminum 26 ground state to excited state of magnesium 26. Why? Because this decay from the ground state of aluminum 26 is having half life of 10 to the power 5 years. So, what? In 10 to the power 5 years, that means we have enough time for the gamma ray to escape from the star and reach the Earth. Are you getting what I am trying to say? Aluminum 26 is decaying to the first excited state of magnesium 26, whose half life is 10 to the power of 5 years, about 1 million years, and this time is sufficient for gamma ray to not get absorbed within the star always. It can always escape from the star. Not only escape, they can reach the Earth. Not only they can reach the Earth, it is indeed reaching the Earth, and we are able to detect the gamma ray 1809 keV. I really want to show one photographic evidence to support this statement. Okay? This is the all sky image of aluminum 26 gamma ray emission at 1809 keV as derived from a 9-year survey. See, for 9 years people have collected the data using Compton instrument on board the Compton Gamma Rays Observatory. So, Compton, I think you might be aware, he is the one who proposed the way gamma ray interact with the matter, that is a scattering process. Okay? Anyway, so in this picture galaxy is considered at the center, fine, and this green and yellow, I mean red region, they shows the existence of gamma ray of energy 1809 keV, and this 1809 keV is the unique signal of aluminum 26, nothing else, alright. And if you see the production rate of this gamma rays from the aluminum 26, interestingly it is about 2 times mass of the sun. Okay? And what is the site of this process? See, throughout this course one has to explore or try to understand at which site this is happening. Is it immediately after the Big Bang, or within the star in the initial stage, or in the supernova, or in some other place? So, one has to look into the sites of various processes. So, that is what this course is all about. Not only the energy production in the stars, not only the nucleosynthesis, but also the sites of these nuclear processes is also interesting and important to understand. So, coming back to this, the site of this aluminum 26 gamma ray is type 2 supernova. So, we have type 1 and type 2 supernova, which I will explain later. Okay? Basically, supernova is nothing but an explosion stage of the star at the end of the star. and during explosive carbon and also during neon burning. Do not worry about this explosive carbon and neon burning stage. I will cover these topics in due course. Okay. So, the point which I am trying to highlight in today's lecture, last lecture was fully on the discovery of technetium, and today's lecture is fully on the discovery of aluminum 26. And if you have not heard of decay scheme, so called decay scheme of a radioactive source, I am sure you might have got some idea about the decay scheme of some source, and especially aluminum 26, and how the transition is taking place from aluminum to magnesium, and the half life of the aluminum 26 ground state to the excited state of magnesium, half life is around 1 million years, and that time is sufficient for the gamma ray to escape the star and reach the earth. We are able to detect. The conclusion, because we are able to detect the gamma ray, that means synthesis is happening in the stars. It is very recently, 1 million is very recent scale at the cosmological level. Cosmological level, I said many times, it is billions of years. So, 1 million years before, if something is happening and we are able to detect, that means the nucleosynthesis is a continuous process in the stars. It is still happening, and at any time of the time, here you can detect these lines. Of course, if you choose the experimental setup appropriately. Thank you very much for your attention, and in the next lecture I will cover 2 more evidences of nucleosynthesis, and then I will move on to the actual part of the nuclear astrophysics. Okay. So, these are lectures which are covering, initially I have covered astronomy, that is observations, and then explanation of the observations, that is astrophysics, I have been discussing in these classes. Thank you very much for your attention. See you.